Today's lesson is lesson 1.4, graphs of functions. We've been talking about functions in class, and we're going to be more specific, and we're going to learn about graphing them and also what a real function is. So a real function, it's a function whose independent and dependent variables, so we've been talking about those in class, they stand only for real numbers. I'm going to go through an example from driver's education. When a driver attempts to stop a car, the distance d the vehicle travels before stopping is a function of the car speed x and can be modeled by the equation d equals x plus x squared over 20. If we gave the name c to the function, we're going to call it c, giving the stopping distance, then c of x equals, and they missed that x in there, x plus x squared over 20. And here you can see on this table here, speed equals x, and we have 0, 10, 20, 30, 40, 50, 60, all the way up to 70. And then the car's stopping distance in feet equals c of x, and that's 0, 15, 40, 75, 120, 175, 240, and 315. If you look at the graph of that function, as you can see, as the speed that's on the x-axis here, and this is a car's stopping distance graph right here. Speed is on the x-axis, distance is on the y-axis. You can tell that as speed increases, the stopping distance increases as well. If you also look at the graph on the right, it's a car versus an SUV stopping distance. The blue line is the car, and the SUV line is the red line. So the SUV has a different function. You can see x plus x squared over 12 instead of over 20, and its stopping distance increases as its speed increases. That's why the red line of that graph is higher than the blue line. Probably has to do with the weight of the vehicle, if you would think about that, probably. Okay, let's talk about domain and range and set builder notation. Some more vocab words for this lesson. If we look at domain, we can compare it to the graph. The domain is the set of values for the independent variable, and that's typically the x values. So the domain for that car stopping distance graph would be the speed. That would be the x values. So if the domain is typically those x values or that independent variable, then the range is going to be the set of values for the dependent variable, and that's typically the y values. Or in the case of the car stopping distance graph, it would be those distance values. And finally, set builder notation is just the way that we're going to write that domain and that range. It's just a way to write it. So we can say the notation, and we use a brace, and then we say x, and then a line, and dot, 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 and another brace. And we read it as the set of all x such that, and dot, dot, dot. And I'll show you an example down below on how you would write it and read it. So in our example, the set builder notation for the domain would be, so from that car stopping distance graph, we would say, and we would put a brace and an x and a line, and we'd say 0 is less than or equal to x, less than or equal to 70, and another brace. And we would read that as, for that domain, it would be the set of all x such that x is greater than or equal to 0 and x is less than or equal to 70. That's how we would read it. We would write it like I wrote on the line right there. And the range would be, so those are those dependent value variables or the y values. We would write a brace, and we would put a y and a straight line, and then the range from this example, it goes from 0 up to about 315. So we would say 0 less than or equal to y less than or equal to 315. And we would say the set of all values such that y is greater than or equal to 0 and y is less than or equal to 315. If we go back to those domain values, those x values, if you look on the graph again, the car stopping distance graph, x goes from 0 up to 70, so that's how we got that 0 to 70. So it's always not the same numbers, it just depends on the graph. You have to look at the x values for the domain, those independent variables, and the y values for the range or those dependent variables, and then you would write it in set builder notation like we just did at the bottom here. Okay, now we're going to talk about different types of numbers, and that I think will help you explain because we've been talking about real functions, so we're going to talk about real numbers. But we're going to actually work our way up the chart on this one. So we're going to talk about naturals first, which is at the very bottom. Natural numbers, you can also call them counting numbers. So how would you typically count? You'd start with 1, 2, 3, 4, 5, and so on. Counting numbers do not include 0. So not 0. Those are counting numbers. So that's why we have the naturals down here on the chart, 1, 2, 3, 4, 5, and so on, and then we have 0. Those all are non-negative integers or whole numbers. So as we're working our way up the chart, we have non-negative integers or whole numbers. That would be 0. So that would include 0, and then 1, 2, 3, 4, 5, and so on. That would be non-negative ones, whereas negative integers, they would be the negative side of it, like the negative 3, 2, 1, and so on. Because integers are negative and positive numbers. So we could have -3, -2, -1, 0, 1, 2, 3, and so on the other way. Those would be integers, negative and positive integers. So we have talked about negative integers would be that -3, -2, -1. Non-negative integers would be like 0, 1, 2, 3, 4, and so on. That moves us up to integers, which we just talked about. That's including negative and positive. Non-integers over here on the right. They have digits to the right of the decimal place. So for example, you could have 15.322 or 0.22 or 1.53. Anything that has digits to the right of the decimal place. Because we know integers are just whole numbers like -3, -2, -1, 0, 1, 2, and 3, whereas non-integers have decimals basically. We're moving our way up then to rational numbers. Rationals are real numbers that are not rational. Oh, I'm sorry, that's irrationals. Let's back up for a second on that one. Okay, rationals are numbers represented by ratios of the form a over b, where a and b are integers. Okay, you can see I wrote the definition in there for rationals. So it's a ratio, a over b, but b cannot equal 0, and I wrote that down there because then it would be undefined. For irrationals, then I already gave that explanation. It would be any real number that are not rational. So some examples of rational numbers would be, let me write it down here further. I'll draw an arrow. 1, -7, 2/3, square root of 16. Whereas irrationals, they are not rational, but they are real numbers. And then some examples would be pi, square root of 5, and square root of 10. Finally, we have real numbers. They're positive or negative, large or small, whole numbers or decimal numbers. So it's kind of a big grouping. So I wrote that definition for real numbers. It's basically everything in here. So that's why we started from the bottom and worked our way up to the reals. But the reals is the big grouping. So positive or negative, you've seen that in all the different areas. In integers, you have negative numbers and positive numbers. Large or small, you could have decimal places, like in the non-integers. Whole or decimal, like I said. So definitely you need to learn all these types of numbers and how they, where they fall underneath each other.